In this video, we're going to take a look at the drag force and terminal speed and how drag and air resistance can determine our terminal speed. So let's first start a fluid. A fluid can be any type of gas or liquid. All right, so anything that can flow, we consider a fluid. And so when you're in a fluid, if there's a relative velocity between a fluid and an object, then there's going to be some type of drag force. There's going to be some resistance through that fluid. So the properties of a drag force, it opposes the relative motion and points along the direction of flow relative to the body. So the direction here is along the direction of the flow, typically in the opposite direction. It's kind of like a friction force. Oftentimes we'll even call drag the air friction, so to speak. So here we're going to examine the drag force for air, all right, and that's going to be the most typical one because air is a fluid. When traveling through it, we do experience some type of drag. So with a body that is not streamlined. Now, what does it mean to be streamlined? That's something that is very aerodynamic, all right? And we'll talk about what constitutes something that's aerodynamic. And so for motions fast enough that air becomes turbulent or breaks into swirls. Now, we're not going to get into the physics of this breaking into swirls because that's actually a lot more complicated, the math, and you need kind of some Calc 3 and Calc 4 concepts to really quantify how air becomes turbulent and breaks off. But we're just going to look at the results of that and how, okay, we see this drag force. We see some decrease in our acceleration, and that's what we're going to look at here. So drag can be calculated by this formula. All right, drag is equal to 1/2 c rho AV squared. Now, what do all these things mean? This is a very new looking formula that has some different stuff in it. So first off, the V is the relative velocity. So the first thing that this should tell you right away is that, hey, now wait a minute, the faster I go, the greater the drag. And so the drag is dependent upon the velocity, and this is why we speed up to a point until we reach terminal velocity when we're falling, because our velocity gets so high that our drag force is equivalent to the gravitational force pulling down. And this is what allows parachutes to guide paratroopers down in a safe landing. Well, why does a parachute help as opposed to just a body falling? Well, that's because the area, the cross-sectional area, matters here as well. And A is the effective cross-sectional area that a body has, the area taken perpendicular relative to the velocity. A parachute, very big area. A person falling through like a pencil dive, very small area, so you're going to have a small drag force. That's what we call streamline. Okay, there are a couple other things that are important here. Rho, which is the air density, so whether we're moving through air or moving through water, the density matters. The more dense the fluid is, the greater the drag. And this should make intuitive sense. Falling through air, you're going to move more quickly than falling through water. Water is going to be more resistive. C is the last thing here that is kind of new. This is an experimentally determined drag coefficient. Okay, this is very much like mu, the coefficient of static friction or the coefficient of kinetic friction, except this is the drag coefficient. Now, this doesn't necessarily mean it has to be between 0 and 1 like mu does, but it's just it's experimentally determined. Now, in reality, C is not constant for all values of V. C actually has a little bit of dependency on V, but for our purposes, we're going to keep it constant. And it's going to be based upon the shape. All right, how aerodynamic is that shape? You have a ball that's falling through the air as opposed to a cube that's falling through the air. I mean, obviously, they do have different cross-sectional areas. However, we could design a ball and a cube to have the same effective cross-sectional area, but one's going to experience more drag than the other because it's not as aerodynamic. And that is where this coefficient here, the drag coefficient, comes into play, C. So when looking at something that is falling, we see that we have the drag force minus the force of gravity. That is equal to its mass times acceleration. So if we want to look at, well, when do we reach this terminal speed when we're moving at a constant speed? Well, this goes away to 0, And so we just set those two equal to each other, and we can solve for our terminal speed here to be the square root of 2 times the weight divided by C rho A, or the cross-sectional area there. So terminal speed can be increased by reducing A. All right, so reduce the cross-sectional area, you're going to fall more quickly. All right, and you'll have a higher terminal speed. Or we can decrease it by increasing A. So a parachute, we want to decrease our terminal speed so we don't break our legs when we hit the ground. So we have a big parachute. Increase the area, that will decrease the terminal speed. So skydivers use this to control their descent, this idea of the area. You know, they bring their arms out to slow things down, bring their arms in to speed things up because they're changing their effective cross-sectional area. So the speed of a raindrop is actually affected by this drag idea, and actually the shape of the raindrop is as well. And so if we want to look at the force of gravity, we can express that in terms of the mass times baby g, but we can get the mass by the volume times the density of water. Okay, and the volume, well, if it's spherical to begin with, we get 4/3 pi r cubed, and then times rho times g. And so we plug things in here to find what is the terminal speed, and using the fact that the cross-sectional area would be a circle, which would be pi r squared, we can get the terminal speed is about 7.4 meters per second, or 27 kilometers per hour. So that's the fastest a raindrop can drop, whether the cloud is closer to the surface of the earth or the higher to the surface of the earth. That's as fast as it can go based on the drag coefficient. Now, because of that, we actually get this raindrop shape that isn't spherical because of that drag.